Greetings and welcome once again to Chemistry A, Mr. Picard, stay home, stay safe, chemistry class. And actually I am home alone, so I don't need the mask. The camera's here with me, and I think you're at least 6 feet away, so we don't need the mask again. And today I want to make some models of molecules, and in particular I'd like to model the combustion of hydrogen reaction that we did previously. And why do we make models? There's a lot of reasons. One reason we do in chemistry is that atoms and molecules are generally just so darn small. Atoms are always very small. There's some pretty big molecules, but the other thing is just to keep track of things. In order to see them and visualize them, we can sort of sort them out. And that's really important to understand how substances come together, break apart, and form new substances. So in the classroom, we use something like these pretty often. It's generally called a stick and ball model. But they're not perfect. They're good. They're easy to work with, to snap together and snap apart. But so they're useful, but atoms really aren't perfect little spheres. Certainly bonds aren't, I took the nose off the poodle. Bonds aren't little sticks, but they do represent the connection, so I think that makes sense, the bond between in this case, hydrogen, carbon, and oxygen atoms. And so modeling is useful. And you're going to make some models today, or soon, but not probably using these because these kids are at school, so we'll get rid of those. I mean, one question we might have is, why things bond together. And today we're not going to get into the big reasons, but we could take my marshmallow model. This is one we've done in school. I've done it with students. It's sort of fun. So 2 big marshmallows. I've got 2 bonds represented by 2 toothpicks because it's a very strong bond. And what's really going on here is these 2, maybe they're oxygen atoms, when they come close together, they can share their energetic burden, in this case the burden of carrying electrons. So when they share these electrons by getting close together, they move together and they bond. And they can exist with little less energy. They're a little bit lazy, so to speak, and so they come together. And the other element we could make with our marshmallow, which you could do at home too. These are the small marshmallows. Here's a green marshmallow. I'm not sure they actually taste different, but they're different colors. And we'll use the smaller marshmallow to represent hydrogen. And it actually bonds for the very same reason. When it gets very close and shares an electron with another hydrogen, it can do so more or less energetically. So it will stick together in that sense. There is something unique about these 2 in that there are only 2 atoms bonded together. In this case, it's the same type. And we have a word for these types of, a term I should say, and it's called diatomic. I've also posted this for you so you can look up the definition. But a diatomic molecule is actually 2 atoms that are bonded together, and sometimes they're the same, let's say like 2 oxygens. Sometimes they could be 2 different types of atoms, but only 2. Example comes to mind would be chlorine and hydrogen, which would form hydrochloric acid. And that is sort of unique about our reactants, which we're going to model. Both of our reactants were gases, and both of them were diatomic. And I think you kind of might know this already. I mean, let's bring out. Let's make another one. How about we make a diatomic my first idea for you guys was using these candies called dots. And they're kind of these gummy candies. So we'll make a diatomic, we'll call this diatomic, the red one's oxygen again. So here is a diatomic oxygen as a dot model. Oh, we should probably put, since it bonds doubly and shares multiple electrons, let's put 2 bonds in there to show that the strength of that bond. There you go. We can also help with naming this by making models and coming up with, in our quest to keep track of things in an equation and formula. And I think this is the one I thought you might know. Hey, I need some O2. Well, yeah, some oxygen. O2 as a gas in our atmosphere almost always exists as a diatomic molecule, 2 bonded atoms of oxygen. There's a few exceptions to that, but this is what we usually find. So I'm going to have you guys make your own models, and we're going to do some manipulations of them and answer some questions with them. But I was trying to think of stuff that you could do at home. So we have marshmallows, we've got dots, but then I thought we should have some healthy choices. Everyone's always talking about healthy choices. So I got this idea for tomatoes. Maybe getting like cherry tomatoes, and they make red ones, and they grow red ones, and there's also these yellow ones we could use. But the thing about those is they're a little bit, I'm not going to recommend the tomatoes. So I moved on, and I was thinking, I think what might work is grapes. And so let's take some grapes, and we're going to form a molecule. And we'll have a red grape representing maybe one type of atom, and maybe we have a green grape, and let's see, we'll stick another green grape on there. So there, we have some sort of, pull the stem off, it looks better. Okay, so there's some other model that we could have made with grapes. We could have the green grapes represent one kind of atom, the red grape another. So we could make a grape molecular model. But my favorite, I decided, was this. Strawberries. So we'll have a strawberry, let's say in our reaction, I want to make diatomic oxygen. So nice big average atomic mass of 16, big old strawberry, and it's going to bond doubly with another strawberry. So now I've got diatomic strawberry. Or maybe we can use it to represent diatomic oxygen. And so I think that could work. And then I was thinking, what about the smaller, blueberries that we have? So what if we bonded a couple of, or rather smaller hydrogens? And I thought of using blueberries. There you go. And I think I'm going to use 2 hydrogens here and stick this. So now, what do we got here? We've got blue 2, strawberry 2, or B2, S2. I'm counting up these 2 and these 2. So maybe that could be, it definitely could be a model for a particular substance. It is a model of a particular substance. Oops, there go the dots. That's okay, I'll clean that up later. What I'm going to do is post a quiz and also kind of a worksheet that you can look at first. And let me clean this up. The second page of the worksheet looks like this without the tomato seeds. And one side is a big square, and at the top it says reactants. And this is where I'd like you to set your model, whatever you come up with, on the reactant side, and either sketch it or you can take a picture. And then there's an arrow, which is the yield sign, meaning the reaction takes place. And then I'd like you to put your products, whatever they happen to be, on the other side. And you can take a picture or you can sketch them. And we're going to use the models to help answer some questions about what happens in a chemical reaction and how we can keep track of it via models and chemical equations. All right. Hope you're doing well, and I'll see you in the next video.